homework 15, page 419, section 7.4. So we're skipping 7.3 because 7.3 is just logarithms. Like, I mean, nothing with calculus. It's, you know, this is where calculus comes back in. So we're jumping to 7.4. Number 3 through 25 odd, 33, 37, 45, 49, and 51. Okay. So here, this is not all one thing. These are separate functions. I just don't want to write f of x equals for each one of these. So this is a function, this is a function, each one of these is a function. And what we're going to do is take the derivative of each one of these. We're going to start on the easy side. What's the derivative of this?
Yeah.
So wait, well, the 1/3 is there. Yeah. And so the 3 drops down, and that's why I did that. And then we demote this guy by 1, and so it's just x squared. Okay. So now, what's the derivative of this guy?
X.
Just plain old x, because the 2 drops down, kills the 2, bring it down to 1. What's the derivative of this guy?
1.
Just plain old 1. We can see that a couple ways. It's x to the 1. So the 1 drops down, we get 1x to the 0, which is 1 times 1, which is just 1. Or we could be smart about it and say that function has a constant slope of 1. What about this? What's the derivative of that?
0.
0. Again, we can see this a couple different ways. That's the constant function 1, therefore its slope is 0. Or we can, and this is where it kind of breaks down, this thing, where we say, well, that's 1 is the same thing as x to the 0. And so if we use our rule, the 0 drops down, and then it's to the negative 1, but 0 times anything is 0. So, yeah, but that's kind of where that rule breaks down, kind of. It still works, but who cares? That's not really the point of this. What's the derivative of this guy?
X to the negative 2.
X to the negative, because the negative 1 comes down, kills the negative, and then we demote this guy by, I don't think I've ever said demote before. I don't know why I just started saying that, but that's what happens, right? What about this guy?
X to the negative 3.
To the negative 3, because again, the negatives kill each other, the 2 kills the 2, we bring him down by 1, making it negative 3, and then finally, what do we have here?
X to the negative 4.
X to the negative 4. X to the negative 4. Okay, so now let's just look at this line right here, that all the stuff we just derived. Who's missing? We're missing something, because if you think about it, and we could imagine that this goes on forever in both directions.
Oh.
We have,
It's like a pattern.
yeah, there is some, right? So like you could imagine going this way, you'd have x squared, x cubed, x to the 4th, and so on. And you come down, you have x to the 0th, 0 itself, and then negative 2, negative 3, negative 4, negative 5, all the way down to negative whatever. There's no x to the negative 1. X to the negative 1. And so this is what we're gonna think about this for a minute. What we're looking for. So what we did is we took a function and took its derivative. And right now somebody's missing. I'm wondering what function, I'm looking for a function, f of x. What does it equal? Where I take its derivative and it gives me x to the negative 1. And I'm looking at all these, like, we didn't miss anybody here. Maybe if I threw in a 0 there, but the derivative of 0 is just 0. We have all the powers, and you could try, if you're like, oh, maybe it's like a fractional power, right? Maybe if I had x to some fraction, and I take its derivative, I guess the p and the q would come down, and then we'd have x to the p q minus 1. And you could say, you know what? Maybe I'll solve that. I'll say, for what values of p and q give me a negative 1? And so we add the 1 over here, and we have p over q is 0. Oh. Well, that doesn't work, because that's to the z. That's not there. So we're missing something. It seems to me like there should be a function where you take the derivative of it and it gives you x to the negative 1. So what I'm just gonna think about this and say, well, I may not be able to just think off the top of my head what it is, but what I can do is say, you know what? If I have the derivative, let me just graph the derivative itself and then put together what f of x must look like from the derivative. And so if f prime of x, if its derivative is 1 over x, which is this guy, here's f prime of x. Now let's see what f would have to look like. And now again, right, anytime you take a derivative of a function, so like if we have f of x equals x squared plus any constant, right, when you take the derivative of it, that constant goes away, right? So you have f prime is 2x, and so you've drawn, let's say we draw our derivative, f prime is 2x, and we could piece together what f would have looked like. We just don't know how high up or down we've shifted, right? Like if I do this right now with f prime, trying to reconstruct what f looks like, I'd say, okay, well, I guess its derivative here is 0, but I don't know if that's up here, if it's down here. I'm not too sure, but I do know that once we go, now it's positive over here, so it's a bit more positive, so it does something like this. As we go here, it's negative, a bit more negative, and so on, and so it could have been this, but it very well could have been this too, right? And that comes back to the idea of like, well, it depends on what the plus c is. So as we do this to try to reconstruct what f is like, we have to remember whatever picture we end up with, it might be shifted up, it might be shifted down. We don't really care. It's just, I want to get an idea of what that thing would look like, and then to get an idea of what this might be. I don't know what it might be, but maybe by drawing a picture we could get an idea, take a guess, and see if it works. So does that make sense, my plan of investigation here? I have no idea what this thing's going to look like. I know it could be shifted up and down, but maybe I'll recognize it and say, and that might give me an idea. I want to draw this a little bit bigger. So we know that f of x is 1 over x, and we're looking, f prime of x, and we're trying to figure out what is the original function that did that. And so what I'm doing, I'm going to try to reconstruct the function by looking at its derivative. So here's its derivative. It looks like this. And for right now, I'm going to ignore what happens over here. We'll get into the negative stuff later. Right now, I just want to look at this part. And so one thing I could see is, now I know that this is 1 over x. So right here, when I plug in a 1, I get out a 1. So its slope here at 1 should be 1, right? It should look like x when I plug in a 1. And I could, again, I could make this arbitrary. I could go anywhere up or down. Why don't I, since I know what this is, why don't I just start here at 1? And I could say, okay, at 1, its slope is 1. So I'm going to draw a 45 degree angle right there. Now, as I move this way, its slope gets steeper, right? I move over, its slope gets bigger, right? I move over by half, its slope goes to positive 2. So I go over some, its slope should be steeper. I go over more, it should be even steeper. It's this kind of thing that's happening until it gets like really, really big, right?
Yeah.
As I move this way, its slope gets shallower, right? Because now we're here at a half, and now the slope is a quarter, and now the slope is an eighth, now the slope, and so on and so forth. Now I could kind of connect these dots and see, okay, well, obviously we have an asymptote as we go this way, because the slope keeps increasing, increasing, increasing. It goes, we know it jumps up to infinity, and so clearly we're going to have some kind of asymptote, and it looks like that asymptote's going to be there at 0. So basically what I'm saying is I'm going to connect these dots like that. Does that look like any function you've seen before?
Does it look like log?
It looks like log. And we could use any log. I mean, we don't know, but I'm going to assume. Like, if I'm going to play with anything and take a guess, I'm going to just assume natural log because, well, we'll get into that in a minute too. But So I'm just going to assume maybe the function that I'm looking for, I don't know, it might be log. So that's the question. Is this natural log of x? So what I'm going to do then is to see if this is the case, I'm going to take the derivative of natural log. And so, okay, I'm assuming that f is log x, and I'm going to figure out what is f prime of x. By definition, f prime is the limit as
h goes to 0
of
f of natural.
wait,
F of x plus h.
f of x plus h
Minus f of x.
minus f of x
Over h.
all over h. Now, which I'm going to rewrite now with the actual value of the f that I'm thinking of.
Natural log of x plus h.
Natural log of x plus h.
Minus natural log of x.
Natural log of x
Over h.
over h. Now, I'm going to go ahead and jump to the chase here because it will be helpful if I do it this way. Yes, h, that's what it is, that's the distance. But if you remember how we get that, it's we take x plus h minus x. And yes, that reduces down to h. Sometimes it's nice to write it this way. You'll see why in a second. Now, we could stare at this all day. The thing that we did with e, it turned out that e to the x plus h, we could rewrite that easily as e to the x times e to the h. We don't have a similar property with logs. Like, if it were log of x times h, then we could rewrite that as log x plus log h. But we don't have a nifty property that tells us what to do with adding in here. So we can't rewrite that to maybe do something.
You put an e underneath, doesn't it?
Yeah, but we can't. But how are you going to do that, right? Like, good luck. So what we're going to do is this. So first off, let's get a couple, yeah, we'll just do this first. What do I want to do? So I'm going to get rid of this stuff here. And let's just think about what log is, the natural log. So here's this statement. Remember how we defined it a couple years ago. Y of natural log, natural log of x equals y means the exact same thing as, so remember, log is the inverse of the exponential function. So you plug the input into the exponential, the output that you get, to undo that, right, you swap the roles of inputs and outputs. So if the input is x and the output is y, that means the same thing as the output goes into e gives you your original input back, right?
Yeah.
That's what that means. In fact, that's how we defined log x. We said log x is the function which gives you back your original input. In pictures now, and this will be important to get our heads around what's going on. Here I'm going to draw, this is y equals natural log x. And we've just set up a difference quotient, right? We said you go to some value x and you plug it in, and what pops out is natural log x. Then you go to some distance beyond it, call it h, and you go to x plus h, plug that in, and out pops some output, log x plus h. Is that legible? Can you see that? That's what I did? Okay, all right. Now, we can also think about that as, well, okay, that whatever log of x is some output, let's call it y, right? And so, now the inverse of this thing, remember, we're just going to swap the roles of x and y. And so if I had this like a sheet of paper, I would flip it this way, right? Where I make this guy go up, right? Old positive inputs go to new positive outputs. old positive outputs go to new positive inputs. And I draw it, this function would look like this. This would be x equals e to the y, right? So this was my x-axis, this was my y-axis, this is now my y-axis because I flipped him over, right? I rotated it over the line x equals 1, and it gives me this. And so now, this thing here, y, whatever that output was, y, when I plug him into the inverse, he gives me back the number where I started. He gives me back x, which is the same thing actually as e to the y. I'm going to write it like that. You plug in y into this function, what do you get out? Well, whatever e to the y is. But by the way we set this up, by the definition of log, that means that this number is the same thing as x, right? Okay, so nothing new is going on here. That's just x. Now, here's the thing. This is also some number. I could call it z. I could say log of x plus little h equals z. But the thing to notice here is that there is also some height difference here. There is some change in height from here to here. Now, I'm going to call this height capital H. It has nothing to do with little h. They're not the same number. And you could probably see that, right? Like, this is bigger than that. You could probably find some relationship, but that's not the point here. So whatever this output value y is, there is some increase, we'll call it h, so that this z, whatever it happens to be, is y plus h, whatever that h happens to be. Do you agree? Okay, so whatever that height is, we could rewrite this as whatever y was plus whatever h would have to be to get that, right? Yeah. Okay, so we're good there. So, okay, on the other hand, if you take that z, that output value from log, which is the same thing as y plus h, and you plug him into e to the x, so we take our y plus capital H, plug him in, the thing we get is e to the y plus capital H. But that right there, the whole reason that we got it in the first place is because we plugged in x plus little h into this function. So that means that that is the output that you get back, right? You get your original input back as an output from the inverse function, right? You with me on that? Okay, okay, all right. So, now, let's just see. Let's just see what happens. We just said that log of x plus h is some number y plus some number big capital H. Okay, so this is the limit. So I'm just going to rewrite this. Maybe it'll help me, maybe it won't. But I'm going to call this y plus big capital H minus log x is the thing that we're calling our new y, right? Right? Okay. X plus h down here, that now we've renamed that. X plus h is now e to the y plus capital H minus x, which was this guy right here, e to the y. Now there's no little h in here, right? So it doesn't make much sense to say as little h goes to 0 right here. But what happens to big H as little h goes to 0? It also gets smaller, right? And you can imagine as h goes to 0, these things are linked, right? These points are linked together. Whatever you plug in here comes out here. And so if you make this smaller, this guy moves this way, making big H get smaller. It's the same thing right here. So we could consider this in two different ways. Either you're making this H smaller, but that forces, if you do that, that forces that guy, because these are functions, right? Make this H smaller, that brings this input over. But what is this in the first place? Well, it's just the inverse of this. It's the exact same picture. They're linked together. So as you make big H small, you make little h small. Or as you make little h small, you also make big H small. They're the same thing. You buy that?
Yeah.
Okay, now. So this is the same thing as the limit of big H going to 0. Now the top reduces, y plus h minus y. The y's cancel, we're just left with a big H. Okay, and now this right here, this, well, we dealt with this last time. In fact, this is the same thing we had last time. This is just e to the y times e to the big H minus e to the y. I can factor out my e to the y, so let's do that. And this time I'm going to keep them inside here. I know I pulled it all the way out last time, but who cares? It really doesn't matter. E to the y is right there. And now we have e to the h minus 1 left over. Well, again, we're in the same situation as before. We have some number, we have a limit that's going to 0, so we could do that nifty little trick where we say, okay, hold up. E itself is defined as, so we have e raised to the h minus 1. E is defined as the number that's limit does this. 1 over h, right?
Yeah.
So e to the h is the same thing as this thing to the h, which we saw last time, right? The h comes in, it cancels that h. This is the same thing. Limit as big H goes to 0 of big H e to the y. That works out to, so 1 plus big H, h over h, which is just 1, so that's just 1 plus h minus 1. You buy that? Limit as big H goes to 0 of h e to the y times, only thing left is h. H's cancel, and we just have a constant e to the y, 1 over e to the y, and so this just works out to 1 over e to the y. Now, wait a second. Okay, so are we good up to here?
Yeah.
Right? It's really, like, this is just the, this is just, we just took the old, like, this is the definition, this is how we found the derivative of e to the x, but we just flipped it, and instead of calling it x, we called it y. It's just 1 over that. Now, I'm going to get rid of all this and write this right here. Do you buy that? I mean, right, we could just take that out and put them in the, out there, the limit's 1, and all we're left with is this. And so, okay, this works out to be 1 over e to the y. Now, but we have a problem. We have a slight problem. It's not much of a problem. Is that, here's the problem. We don't care about y. We have f prime of x is equal 1 over e to the y. That y is not there. I don't know what, if you gave me that, if you said here's my function, g of x equals y squared. Well, I don't, what is y in relationship to g, right? And so, is there something on the board that tells us what e to the y is?
X.
It's just x, right? Because by definition, that's what this is. Or we can also see like all of the little reasoning that we did here. We said, well, you plug in x and you get out some number, okay? Well, let's call it y. But whatever that number is, when you plug him back in, yes, it's e to the y, but that's your original number. It's x. And so we could say that is 1 over x, which is x to the negative 1, which was the thing we were looking for. And yes, indeed, the derivative of the natural log does give you 1 over x. That's pretty cool. Okay, so you got that? Okay. Now what are we going to do with all this stuff? So, that's something you're just going to need to know for the rest of your life. Now let's get into some stuff that it could have gone into the last lecture, but I wanted to hold off until we got log as well because these two things go together really well. Oh, wait. Yeah. Let me show you how your book does it. The book does it. It's so much cleaner. But I mean, I like the idea of going with the definition of a derivative and reasoning through. What you could do is this. You could say, well, this is what log is. It means the same thing as this. Therefore, if I want y prime, I could use implicit differentiation over here. Now, right-hand side is easy. What's the derivative of x with respect to x?
1.
It's just 1. What's the derivative of this with respect to x?
Y times e to the y minus 1.
Whoa.
Wait, no, sorry.
No, because that's not a...
E to the y.
So, yeah, the derivative of e to the stuff
Yeah, it's just
is e to the stuff. But then, we have to do what? Multiply by the derivative of that
Y
stuff.
prime.
So y prime. Oh, that's the thing I'm looking for.
Oh.
Y prime is equal to 1 over e to the y. E to the y is x. 1 over x. That's how your book does it. Much easier. Much easier. But I like going from first principles and seeing, like, does it work out? Because, like, I don't know, something about implicit differentiation to me, I gotta sit here and go, are you sure about that? It just seems like a little bit of magic. It does work, and it is consistent with everything. But I like using the difference quotient, which I don't like using the difference quotient. It really does, but it just makes me feel that much more confident that this works. And so that's how your book deals with it, which is slick. So, okay. So we know all about what happens if your f of x is e to the x, or some constant times e to the x, or some constant times e to the x, or some constant times e to some constant times x. We know how to deal with all that. But what if your base is different? That is, what if it's not e to the x, but what if it's some other number, a to the x? What do we do with that? Well, there's a few different ways we could look at this. One way, and this is the way I like to think about it. So let's just, let me just see, I'm going to quiz you here. If I put this in there, what do I put right here? Right, they're inverses of each other, right? Like we just did that, right? No matter what goes into log, the way that you undo that is you take e. In fact, you said something like that, right? When we had this, you're like, well, what you could do, you could, if you took e to this and e to that, well, I mean, I guess you could do the whole thing and then work it out, but then yeah, it would undo all of that. This is the thing that undoes that. So, let me ask you this question. If I write a to the x right here, what do I need to write right here? A to the x. And so, and this is, if you remember, I said this back in Algebra 2, which is like every exponential function is just e in disguise. Every exponential function, I don't care what it is, b to the x, it is e times some constant times x. And if you remember, our favorite property of logs is that when you log of something raised to a power, is that power drops down. That's how I said it, right? And so the x drops down out front, and now we have that. And so let's just rewrite this guy. Say, well, a to the x is just e in disguise. And that's the same thing as x times log a. But log a, is that a function or a constant? It's a constant, because we're imagining here that we have like 2 to the x. And so what we did is we said, well, 2 to the x is the same thing as e to the log 2 to the x, which is the same thing as e times 2 times log 2. Log 2 is just some number. You could think about it as a constant. Oops, it should have been an x. Yeah, x dropped out. That's just a constant. We know how to deal with this. This is the same thing as e to the kx. And so when we take the derivative of it, what happens?
0.
Joe, whoa.
What? Derivative of a constant.
So, well, hold up. So, first off, the derivative of e to the stuff is e to the stuff. So we have x log a. Then we multiply by the derivative of the inside stuff. So we multiply by the derivative of this, which is what?
minus 0 minus
This is not a function. Log A
x
is
so.
just a constant. X is. And so
Oh,
what's...
right, I was thinking.
Yeah, what's the derivative of kx? Some constant times x.
K times k prime times x plus.
Not if it's a constant. Well, yeah, I mean you could go k prime x plus kx prime by the product rule, right? You're making it too hard on yourself, right? Anytime you have a constant times a function, just pull the constant out. Just pull the constant out, because you're right about this, right? But it turns out that the constant always goes to 0, so this always goes to 0 when you take the derivative, and so it's much easier. And what actually goes through my head is like if I were to set this up as a difference equation, right, or a difference quotient, we'd have x plus h log minus x log all over h and stuff like that. That constant just comes along for the ride. We could pull him out. In fact, we could pull him out of the limit entirely. You could just say log a lim, and then you have your x plus h minus x for h. Oh, it turns out to be 1, right? Like the constant, anytime you have a constant in there, you could just pull him all the way out and just bring him along for the ride. So, back to my question. What is the derivative of x times log a?
X prime times x log
Okay, so then what's x prime? What's the derivative of x with respect to x?
1.
1 times log a. So it's just log a.
Yep.
So if I said, what's the derivative of 3x, what would you tell me?
3.
You wouldn't say it's 3 times x prime, would you?
Probably not.
Probably not. And this is what I'm doing this deliberately because once you see this in your head, you're like, that's a function, I better take its derivative. But once you plug a number in there, right, let's think about what this is. And everybody does this, right? But it's just something you really have to get used to. Once you plug in that number, you have a constant, no matter what it is. It might be 5, right? And so if I said, what's the derivative of x times 5? You would have just said, and I probably wouldn't have written it like that. I would have written it as 5x. You would have just said, oh, it's 5. Same thing here. Okay, log a is just a constant. So, in other words, like your function, x times log a, just has a slope of log a, right? Right, if I graphed y equals mx, you'd say, well, it looks like that. Then if I tell you that m happens to be natural log of a, you'd say, I don't care. The derivative is still, y prime is still just m, right? So it's the same thing that's going on here. I've written it that way because I always put log at the end of stuff that I'm writing. I can't not do that, but it's the same thing as this right here. And so, what is the derivative of x times log a?
Log a.
Just log a. And so, log a, I'm going to write my constant out in front, and we get ex log a. But that's the same thing as this, natural log a, e to the log a to the x. What's e to the log of stuff?
A to the x.
That's just a to the x, so natural log a times a to the x. And so we could simplify this by saying, or like really cut to the chase here, and say the derivative of a to the x is you could kind of think about it as, well, this stays put and a log a pops out. So if f of x equals 2 to the x, f prime of x would be what?
Log of 2 times 2.
2 to the x. There you go. Right? So that's nifty. There's another way of doing this. Do I want to talk about it now, or do I want to talk about it later? No, we're gonna do it later. So there you go. Right? There it is. I'm gonna box it. That's a nifty one to remember. But if you ever forget, you could just do this nifty little trick right here, right? It's like, oh man, what was that? Is it the log? Is it divided by log or whatever? Oh man, I'm not sure how to deal with this. Just do this and go from there. I always forget this. I don't know why. It's so simple, but you could get back to it really easily. Okay, so there's that. And again, that would have been a good one to do last time, but I think it kind of goes well with what we're about to do here. And so I wanted to wait. So, we know how to deal with when f of x is natural log of x, but what if we have a log of a different base? So, right, we want to know what is f prime of x. That's my big question. And what we're going to do is say, okay, well, let's just use the definition of logs here. Say y is equal to log base a of x. That means the same thing as what? What to the what is equal to what?
A to the log of x.
A to the, well, okay, so here's one way you could do it. You could say, and this is usually how I solve it. I say, well, hold up. How do I get rid of that? I take a, so I'm going to bring both sides, raise it, or a, and raise both sides of it. And so then we have over here a to the y equals what?
Log of x.
No. This is the thing that undoes this, right? Just like e natural log x is equal to x,
so
right?
It's x.
It's like, yeah, like why would you take this step in the first place? To undo log a. It's the thing that undoes log a. Or you could just say by definition, right? The input goes to output, so it's just the opposite with logs and exponentiation. If log base a is this, then a raised to the output is equal to the input. That's how you get back to where you started, right? I personally like doing this because this is, I don't know, it seems procedural. This seems like rote memorization to me, but who cares? It's the same thing. You'll get there. So, okay, so that's what that means. Now, there's a couple different ways we could go from here. We could use implicit differentiation. That's going to get a little hairy. I don't like that. What I'd rather do is just take this guy and just take the natural log of both sides. Why? Well, one, because that's what I've been telling you to do since we first discussed what a log was. But also because what this is going to give me is I know how to, do you know how to take the derivative of this now?
Yes.
Yeah, and everybody else, well, now watch what happens. The y drops down. That's our favorite property of logs. And so, because right, like what I'm looking for is what is y prime. Well, that's my goal. And so now I could get y all by itself. I could say y is the same thing as log x over natural log a. One mistake everybody makes is to think about this thing as a function. That's just a constant, log a, whatever a happens to be, right? Like if it's 2 to the y, when you take the log of it, that's y log 2. When you see log 2, you're like, oh yeah, I could plug that into a calculator and get out like 0.693, whatever. Like it's just some number. So this is just some number. And to really make this suggestive, I'm going to just write it like this. There's log a times a function. So there's some constant, whatever it happens to be, times some function. Now can we take the derivative of this thing?
Yes.
Y prime. What happens to the constant?
It stays.
It just comes along for the ride. I'm not even going to think about what it could be. Just rewrite it. What's the derivative of this?
X to the negative.
Yep. X to the negative 1 or 1 over x. And so we could rewrite this if we wanted to. I like putting my x's in front, just times log a. Right? Because that's just two numbers. Multiply them together, you could do it in either order. I just hate having anything on the right-hand side of log. So I'm going to write it like that. And so, there you go. 1 over, it's very similar. It's just like 1 over x, but now we just need to multiply by that log a. Kind of like before, right? When we took the derivative of a to the x, log a popped out, and then that guy stayed put. Now it's kind of similar, right? It's just like the derivative of natural log, but now a log a pops out. So altogether now, we could rewrite that as d dx of, so the derivative of log base a is 1 over x times the natural log of a. There we go. And this is why it's called natural, right? Like it's the that's why we call the natural exponential or the natural log. Is like with natural log, I mean, even if you use this formula for natural log, it would be log base e, and natural log of e is just 1. It's the only one that's kind of unadulterated here. The derivative is just pure 1 over x, right? Every other log has this property that its slope, it's not just 1 over, it's like 1 over x, but it has this constant that you need to multiply by. And good luck trying to calculate what that constant is. All right. you tell me, what's log of 3? Natural log 3. You need a calculator. And so this one's natural. And I mean, it's one of the reasons we call it natural. There's another way of defining everything we've done over last lecture and this lecture. There's another way we could have gotten there. We could have started by defining log and then deriving everything else from it. We could define the natural log as something. We're not ready for that yet, but we'll go into it later. But we could have started there and then derived everything that we know as of right now from the definition of log. But it's perfectly equivalent. Okay, so now what are we going to do? Here is something really, really useful. It's called logarithmic differentiation. D-I-F-F-E-R-E-N. I think I spelled that right. Logarithmic differentiation. You can use it in a lot of scenarios. But here's one where it's really, really useful. We have x raised to cosine x, and we want to find what's y prime. This, by the way, is number 46 from the book. Now you might think, well, I know the rule for this. To take the derivative of this guy drops down, and then this gets, so it would be cosine x minus 1. And you'd be wrong. Because remember this rule that we figured out for the derivative of this guy? Right here?
Yeah.
That assumed that this was a constant number. Remember, because in order to do it, like, we needed to use the binomial theorem, which only works for constants. This is not a constant, right? That's a function. And so you just took the derivative of something and you didn't even bother to multiply by the derivative of the inside stuff. Something's going wrong. You're not doing that right. Okay? So this is absolutely not true. Like, there's something else going on here. How do we deal with it? Well, I'm not about to try to put this into a difference quotient. Could you imagine what that would look like, right? X plus h raised to the cosine x plus h minus x cosine x. Like, you're never, ever going to get out of that. But our favorite property of logs helps us when things are up here.
Log of both sides.
Take the log of both sides. So, not just any log. You could take any log, but it's going to make your life harder because you're going to have some, like, log a pop out. So why do that? So I'm going to do this. X cosine x. Now what do I want to do over here?
Bring the cosine.
Bring the cosine down. Because this is the property of our favorite property of logs, right? And so now, again, now we could just differentiate everybody through by x, or with respect to x. And here we're going to have to use implicit differentiation because, of course, y is indeed a function of x, and that's even explicit. But now that it's here, we got to remember, like we have to treat it like a function of x. So I'm going to take the derivative with respect to x of both sides here. I do that over here, and I do that over here. Okay. So the derivative of log stuff is 1 over stuff. Now what do we need to do?
Times y.
Chain rule, multiply by the derivative of the inside stuff, which is the thing that you're looking for, right? We want y prime. That's our goal. So in our work, y prime had better pop out somewhere. So now, okay, this is a product. Okay, so the derivative of the first thing, what's the derivative of cosine? Negative sine, leave him alone. Add that to leave
Cosine.
that one alone.
Times
It's the derivative of log x.
1 over
1 over x. So I could write it as 1 over x, or I could do like that. Good. Now we need to get y prime by itself. So
divide by 1.
divide what?
Divide by 1 over y, which is just
Oh yeah,
multiplying.
or multiple. Right, there you go. So get that y up in the numerator, and we have. I'm just gonna rewrite this because I don't like minuses in front of stuff. I'm gonna write this as cosine over x minus this stuff, just to give myself a little bit extra room. Cosine x over x minus sine x log x. But y, we know what y is explicitly. And so since we know what it is explicitly, let's get him, because that's not as useful as you might think it is. Especially if I say, what is the derivative at pi over 2? Well, you're going to have to do this anyway, you know, and so, all right, let's just replace it with x to the cosine x times cosine x over x minus sine log. Boom. There we go. There's your derivative. So that's really useful. And not just for when you have like x raised to a power. It shows up in a lot of different ways. But here we go. So I'm getting rid of this. Remember when I said we went through and said that this works whenever this is true whenever n is an integer. And I said it's also true if it's a rational number, right? If n is like, if you have x to the p over q, right? So like x to the 1/2, the way we take the derivative of it is the same way. We say, well, the 1/2 drops down. You subtract off 1 from there and you get negative 1/2. And I also said, you know what, it actually is not just rational numbers, it's also true for any real number. I said that the derivative of x to any constant real number, not like x to the cosine x, right? Has to be a constant real number. But I said like x to the pi works the same way. You take the derivative of it, pi drops down, x to the pi minus 1 is what you get. And you did a bunch of those. I said just believe me, we'll prove it later. We're going to prove it right now. Here's how we're going to do it. We're going to say let y equal x to the n, and let n be any real number. Okay, well, let's take the log of both sides. Take the natural log of both sides. Now what do I want to do?
1 over y times y.
Well, we're not there yet.
Oh, just drop that.
Drop the n down, natural log x. Okay, so now, derivative of both sides with respect to x. This is logarithmic differentiation. You take the log of your thing. Use some kind of property of logs that helps you out. Take the derivative and your life is probably easier. So what's the derivative of log stuff?
1 over y
1 over y
times y prime.
times y prime, which is the thing that we're looking for. And now what's the derivative of this?
1. It's just, sorry. Natural log x. Wait. No, n.
Okay.
And just n. Wait.
So is n a constant?
Yeah.
So let's forget about him right now. Forget that he's there. What's the derivative of that?
1 over x.
1 over x. Now that you figure that out, bring your constant back in.
N over x.
N times 1 over x, or n over x. Okay, so y prime, I'm going to multiply through, we have ny over x. Doesn't really help me out. What was y to begin with?
X to the n.
X to the n divided by x. Can we simplify him at all? If n was 7, what do we do? So let's do this. What's that?
Oh, x to the 6.
That'd be x to the 6th. If it were x to the 3 over x, you would have
X squared.
And so if there's n of them, and you cancel out
N
one of
minus
them,
one.
you have n minus one of them. And n was any real number. We didn't ever need to use the fact that it was an integer. And so this works for all real numbers. For all real numbers. Ha! There we go. So it's not just useful if you need it. I mean, it's useful to prove a cool theorem. Like now we know this works whenever n is a constant, any constant, even 0. I don't think we ever divided by it. I think we're good. Yeah, it works even if it's 0. Although, if it's 0, it's just 1. Easy way. You don't really need to pull out these big guns. But that's pretty cool. Okay, nice. So one more example of logarithmic differentiation. Oh, also, for your homework, you're going to need to remember this. So if you have x, y, let's say, raised to the z, remember properties of logs. Because like I said, with logarithmic differentiation, it helps you do some really cool stuff, but you have to be able to manipulate logs in order for it to work. Because if you just tried to take the derivative of this, and let's say, like, I mean, if it were x times sine x raised to the, I don't know, cosine x, something like that, and you're taking log of that. Well, doing that and then just taking the derivative of it doesn't really help you because, like, you haven't made your life any easier. If you just take the derivative of this, now you have 1 over all of this stuff. Now you have to multiply by the derivative of the inside stuff. Well, that doesn't help your life at all. So the idea of logarithmic differentiation is that you could use properties of logs to make your life easier.
Well,
and if you have a setup like this,
of x plus log of y.
yeah, there you go, log of x plus log of the other stuff, because we have the multiplication right here. And then we could use the further property of log to say this is the same thing as log x. The z drops down and we have log y right there. Okay, now I want to do one more big example to show you how useful this can be. And this is the last one we're going to do. This is number 44. We're going to find y prime, given that y is equal to the 4th root of x squared plus 1 over x squared minus 1. Now, you could see, I mean, we could just plug along and do it. But we have, and what the first thing I'm going to do, I do almost every time that I'm doing calculus, I'm going to rewrite this as something to a power because it's just going to make my life easier. Rarely does it ever not. So I'm going to do that and think, okay, well, if I wanted to take the derivative, okay, the quarter would drop down. I'd subtract off 1, so I have minus 3/4. So it would be a quarter, this stuff to the minus 3/4, then multiply by the derivative of, oh boy, okay, quotient rule, right, or whatever. That would be a huge pain. But if I take the natural log of both sides, let's just see if that simplifies at all. So natural log of this stuff is the same thing as natural log of a bunch of stuff raised to the quarter. X squared plus 1, x squared minus 1. So what could I do?
Drop the quarter.
drop the quarter down. That would definitely be my first step. So that's a quarter log of something divided by something. And so we could break that up. Be careful with this. You make sure you're using parentheses, or I'm going to use brackets. So this thing breaks up into log of the numerator. And you said minus log of the denominator. And now I think we've broken them down good enough. So the only thing to remember is now we have a function in here. And so we take the derivative of that. Whatever's in there goes 1 over that stuff. Multiply by the derivative of the inside stuff. And that inside stuff is, I could deal with that. Whereas with this, it's like, that's my inside stuff. Oh, yikes. I don't want to deal with that. I could deal with this. So log y is here. And I'm just going to take the derivative of both sides here. This is abusive notation, but you get what I'm getting at. Okay. So derivative of log of stuff is 1 over stuff. Multiply by the derivative of the stuff. We have a quarter. Quarter just comes out. Now you notice I'm not using the product rule here. I'm not saying, oh, that's a product. So the derivative of a quarter plus this, plus leave a quarter alone and take the derivative of this. It's just a constant, so I don't even think about it until much, much later. So now, what's the derivative of this? 1 over that stuff.
X squared plus 1
times 2x.
Minus x squared minus 1.
X squared minus 1 times 2x. Okay, a bunch of different ways I could do this. I think it would be, I'm going to cancel these 2's. Well, I'll just do it this way. A quarter. Now we have 2x, x squared plus 1 minus 2x, x squared minus 1. I could get a common denominator. Why bother? I'm going to pull out a 2. Pull out 1, 2. That cancels 1, 2 right there. And so now I have, and I'm also going to bring my y up into the numerator. Okay? Now, y was equal to that stuff. So, okay, y prime is equal to this stuff, the 4th root of x squared plus 1 over x squared minus 1 times a half, yeah, I'll do this, times a half times x over x squared plus 1 minus x over x squared minus 1. And that's good enough. I can pull a half all the way out to the front, but who cares? This is much, I think at least in this case, much easier than if we had just done the product rule, chain rule, quotient rule. Yeah, quotient rule, right, with the chain rule like 1,000 times. So this is a decent, then there are the ones like x to the cosine x, which you cannot do any other way. There's no other way to do that, guy. So there you go. That should be everything you need for your homework, and I think we're done. Unless there's any questions. All right.